Search algorithms in artificial intelligence. Search algorithms can be classified into uninformed search and informed search. Uninformed search can be further divided into depth first search, breadth first search, and uniform cast search. Informed search can also be divided into greedy search, A-star search, and graph search. The issues of depth first search can be overcome by depth limited search. The issues of depth limited search can be overcome by iterative deepening depth first search. Informed search can be further classified into best first search. It includes A-star search. Problem reduction includes AO-star algorithm. Constraint satisfaction, means and analysis, generate and test, and hill climbing. Properties of searching algorithms. Completeness. A search algorithm is said to be complete if it returns at least one solution for a particular input. Optimality. A search algorithm is said to give an optimal solution if it has the lowest path cost. Time and space complexity. Time complexity, time taken by an algorithm to complete the given task, that is called as time complexity. Space complexity means maximum storage space required to perform the search operation. A good search algorithm, it takes the less time and space to complete the task. Uninformed search, that is also called as blind search algorithm, has no additional information about the goal state other than the one provided in the problem definition. The only information they have is on how to traverse and visit the node in the tree. In such algorithms, the machine blindly follows the technique irrespective of whether it's right or wrong, efficient or inefficient. Uninformed search algorithms do not use any information about the problem being solved. They explore the search space blindly without any guidance. This makes them simple to implement but leads to slow and inefficient solution while solving the complex problems. Depth first search. Depth first search, it has three major steps. Explore deeply. DFS, it explores as deeply as possible along each branch of the search tree before backtracking. Stack based. DFS uses a stacked data structure to keep track of the nodes to visit next. Exhaustive. DFS guarantees to find the solution if one exists by checking the all possible paths. DFS procedure. Trees traverse from the root node. The key is searched till the leaf node of the particular branch. If the key is not found, then the search process backtracks to the point from where the other branch was left unexplored. This process is repeated for each branch either until the key is found or the entire tree is completely traversed. Implementation of depth first search. Initialize, push, explore, and backtrack. Initialize, start with the root node and the empty stack. Push operation, push the root node onto the stack. Explore, pop the top node from the stack and visit it. Push its unvisited neighbors onto the stack. Finally, backtracking. Repeat the explore step until the stack is empty or a goal is found. This tree is the example of depth first search. S represents the source node and G represents the goal state. Always the traversal starts from the root node S, then traverses the nodes A, B, D. D is the leaf node, so we have to backtrack it to B and visit the unvisited node, that is E. So E is the leaf node. Once again we have to backtrack to the point, that is node A, and visit the nodes C and then G. G is the goal node. Now we have to stop the execution. Source node to G goal node is S tends to A, A tends to B, B tends to D, then D tends to E, E tends to C, C tends to G. If we are going to traverse the entire tree, backtrack to the source node and find the tree, visit the unvisited vertices, that is H, I and K. K is the leaf node, so we have to backtrack and visit the node J. The entire tree traversal may be S tends to A tends to B, B tends to D, D tends to E, E tends to C, C tends to G, G tends to H, H tends to I tends to K, K tends to K tends to J. Another example of DFS, here we have only 5 nodes. Searching it starts from the root node. So first we need to visit the node 1. So first we have to create the empty stack and push the node 1. So then pop the top of the stack, that is node 1, and visit it. So we have to visit the node 1. Then we have to push the unvisited node, that is 2. So 2 is the another unvisited node, so we have to visit it. So then visit 4. 4 is the leaf node, so we have to backtrack and visit the node 5. 5 is the leaf node, once again we have to backtrack and visit the node 3. The entire tree traversal may be 1 to 2, 2 to 4, 4 to 5, 5 to 3. Another example of depth first search, here we have only 7 nodes. Searching it starts from the traversal, it starts from the root node A, then visit B. B tends to D. D is the leaf node, so we have to search process backtracks to the particular point B. So then visit E. E tends to C. C tends to F. Finally visit the node G. Characteristics of depth first search. Traversal order. DFS visits nodes in the depth-wise manner, going deeper into the tree before exploring sibling nodes. Memory usage. DFS requires more memory than BFS due to the need to store the search path. Completeness. DFS is complete for finite state spaces but may not terminate for infinite state spaces. Advantages of DFS. Memory efficient. DFS uses less memory than BFS as it only needs to store the current path being explored. Finds deep solutions. DFS is good at finding solutions that are deep in the search tree as it explores path to their endpoint before backtracking. Simplicity. It's very simple algorithm to implement. It's a more popular choice for many applications. Disadvantages of depth first search. Infinite loops. DFS can get stuck in infinite loops, especially in graphs with cycles leading to non-termination. Shallow solutions. DFS may miss the shallow solutions if it gets stuck exploring deep paths first. Memory intensive. For large search spaces, the memory requirements of DFS can become prohibitive. Thank you.